Hey everyone, today we're going to be working on the Photogate lab, a very common setup used to measure how fast something is traveling. You'll see it often in the Olympics, measuring skiers, bobsledders. It involves a pretty simple setup of an LED and a photoresistor facing each other. When the object you're trying to measure crosses through the gate, we're able to record how fast that object has been traveling. We have two options for the lab today. We're going to either measure how fast a credit card is being swiped through a credit card swiper, or how fast the coin is traveling down the path. It is common for students to actually adjust this lab for some sort of physics class if you are also taking physics. So let's take a look at the circuitry. For the Photogate circuit, we're only building circuits we have already built in the past. On the right side, we have an LED connected from 5 volts through a resistor to ground. Same thing on the top and the bottom. Both of these LEDs and resistor pairs are hardwired to 5 volts and ground, meaning we can't turn them on and off using digital pins. The 5 volts and grounds actually come from the left side of the screen. The reason we run the wires under the board is because we want to keep the lanes free for whatever it is we're sliding through our gates. The photoresistor circuit starts at 5 volts. We go through our photoresistor, through a regular resistor into ground. In between the two resistors, the photoresistor and the regular resistor, we have a digital wire. The yellow and orange wires go to pin A0 and A1 respectively, and the red and black wires go to 5 volts and ground. That is the Photogate circuit. The Arduino does not have a clock. There's no way for it to know what time it is, how many hours or minutes have passed from point A to point B. But what it does have is a timer called micros, similar to a stopwatch, except you can't start it, you can't stop it, and you can't reset it. It's always running in the background whenever the Arduino is powered. What you can do is record the times at various events. So perhaps record the time at event A, record the time at event B, and by subtracting those two times from each other, we could actually see how long it took to go from event A to event B. And that's what we're going to do here with the Photogate. The next thing we have to do is check our threshold numbers. These are at what numbers does the serial monitor consider our photoresistors to be covered. We do that by opening this very simple code and swiping or sliding whatever we're using in our project in front of our photoresistors and seeing what happens to the numbers. And you can see in our case, the numbers go from 900 down to 400. It's also important to note the direction. So from 900 down to 400, which means we'll pick a number in between, let's say 750, below 750 for us is considered the Photogate was crossed. Every project is going to have a different number, even a different direction, up or down, depending on how you built your circuit. So you have to check this step, get your number, and in what direction the numbers are going. Let's do a quick walkthrough of the Photogate code. So we start with our 4 variables on top. We have start time and end time. That's the first Photogate and the second Photogate. And total time is we're going to subtract the 2, and that will give us the total time of travel. We're going to have serial beginning at 600. We're going to print the speed on the screen. And then we have what we discussed before, the analog read. We're just printing the values from the 2 Photogates. Next, we have pretty much the cunts of the code is we have our first Photogate, analog read A0, and why it's greater than 750. Now, greater than 750 means there's nothing blocking the gate. So essentially, we're waiting for the card or the coin to come. So we want to do nothing. So we have a while loop with nothing in it, except for a semicolon, because we're waiting for our first gate to get crossed. It's above 750 when nothing is happening. All of a sudden a card comes, cuts the gate, and the values go below 750, and we leave our while loop and go on to our first line of code outside of the while loop, where we just record the time that this happened. In the variable start time equals micros, records what time was that first gate crossed. We left our while loop and we record the time that that'll happen. We're going to do the same exact thing again for our second gate. We're going to have a while loop with analog read A1. We're going to be waiting in this while loop, doing absolutely nothing until something crosses the second gate, at which point analog read A1 will go below 750. We'll leave the while loop, go on to line 23, and record the end time, the time that we crossed the second gate. We're going to then subtract the end time from the start time, and that will give us our total time. That's how much time it took us to go from gate 1 to gate 2. The last part is some very simple math. If we we do our distance divided by our time. Our distance in this case is 2.5 inches, and we divide it by our total time. That's how much time it took us to go from gate 1 to gate 2. Now, that math, that formula is inches per microsecond, because the 2.5 is in inches and our total time is in microsecond. So our speed is now inches per microsecond, but we want to know miles per hour. So we multiply by 56,820. How did we get that number? We Googled it. How do you convert from inches per microsecond into miles per hour? Google will give you the conversion number, multiply it in there. The last thing we're going to do is going to print our speed on the screen. Your speed in miles per hour is, that's in quotes, followed by serial print ln of rate, not in quotes. So instead of printing the actual value, it'll print our speed instead of printing the word rate. And then delay 2000 gets us ready for the next run. A pretty straightforward code. Give it a try. So here's what our Photogate looks like in action. We're sliding our card through gate 1 and gate 2, getting our time, doing a little math to convert that into a speed of miles per hour. Contrary to what you might believe, people think they're flinging their cards through at 100 miles an hour. It's actually only 4 or 5 miles an hour. It's a great lab, often used in a lot of different things, in sports, whenever you want to time things, where they're going, where they're coming. Great lab. See what you can do.